part of our discussion with regards to space technology. So in the first part of our discussion, we'll complete the space technology portion. And in the second part of our discussion, we are going to start with a new chapter, which is energy. So that will be the second half, or almost you can say the last 1 hour perhaps of our discussion. So this is what we are going to do in today's class. So we'll start with a topic which has been pretty much in the news, that is Lagrange point. And then after that, we'll go on to discuss all the other aspects of space technology. We'll discuss about ISRO, we'll discuss about a few of the other topics which on and off have been in the news. All right. So these are the things that we are going to do. And then after that, we'll start with our next chapter. All right. So the first topic for us today is Lagrange point. Now, first and foremost, why is Lagrange point in the news? There have been a couple of cases where we have seen that it has appeared in the news for one reason or the other. First, right now it has been because of Aditya L1. It has been because of Aditya L1. Why? The name Aditya L1 basically gets its name from Lagrange point. This L1 basically signifies this point, that is Lagrange point 1. What is Lagrange point 1? We'll just discuss that. So because of Aditya L1, it has been in the news. Before that, we saw the launch of James Webb Space Telescope. James Webb Space Telescope, and this was launched to this point, that is L2. So Aditya L1 has been launched to the point L1. James Webb Space Telescope was launched to the point L2. Then after that, it has also been in the news because there are a couple of asteroids which are called as Trojan asteroids. And there are two Trojan asteroids that we have discovered. One called as 2010TK7 and another one called as 2020XL5. So these are two Trojan asteroids that have been discovered, and these two have been discovered at another Lagrange point, that is L4. So at L4 we have discovered this. So we see that because of all these reasons, in one way or the other, these Lagrange points have been in the news, and they have specially been in the news because of Aditya L1. So first and foremost, we'll try to understand what do we mean by these Lagrange points, what are these Lagrange points, and everything related to it. Now, Lagrange points, you can say in a manner, are very special orbits. All right, these are very special orbits, and these are orbits which will be found, or these are specific points which will be found anywhere, wherever you have a two-body system, where there is one body which is revolving around another body. So, for example, we have the Earth which is revolving around the Sun. So that's why between the Sun and the Earth, we'll see that all these Lagrange points will be produced. Then, apart from that, even for the other planets as well. So, for example, for Jupiter, so between the Sun and Jupiter also there are the same, let's say, 5 Lagrange points will be produced. So that's why for any planet which is revolving around the Sun, this will be produced. Even for the Earth and the Moon, because Moon is also revolving around the Earth. So here also these 5 Lagrange points will be produced. So wherever you have a two-body system where one body is revolving around another body, there are 5 special points which will be produced, and these 5 special points are called as Lagrange points. Now, when it comes to these Lagrange points, why do we say that these are special, 5 special points? So what you will see is, if you look at the picture that we have right here, you'll see that there are 5 points: L1, L2, L3, L4, and L5. Now, all these 5 points will move around the Sun, or let's say they will have an orbit with the Earth. So, for example, as the Earth moves, all these 5 points will also move. So, for example, when the Earth goes from, let's say, this point to this point, so when the Earth comes here, simultaneously we'll see that L2 will also come here. Simultaneously, we'll see that L1 will also come here. We'll see that L4 would have moved to this point. We'll see that L5 would have moved to this point. We'll see that L3 would have moved to this point. So the entire system will be moving. All right, this entire system will be moving. So the relative position between, or relative positions of L1, L2, L3, L4, L5, they'll always remain the same. All right, so they'll not change. So when the earth comes here, so this is basically what will happen. When the earth comes here, L1, L2, L3, L4, L5 all would have moved, all would have moved like this. All right, so this is basically what happens. So we'll see that L1 would have moved here, L2 would have moved here, L4 here, L5 here, and L3 here, and this is where we have the earth. So this is how this entire system moves. How are these points produced? Because of gravitation, because of the gravitational effect of the sun and the earth. This is how we see that these 5 special points will be produced, will be generated. And that's why these points, these are not uh, imaginary points, right? These are not imaginary points, these are points which will be produced, and these are the areas where you will see enhanced gravitational effects. These are areas which will have enhanced gravitational effects because of the gravitational effect of the sun and the earth. Now, why are these points special? Why are we sending Aditya L1 to L1, or why did we send James Webb Space Telescope to L2? What's the reason behind that? Even there are other such missions also which have been sent to L1, L2, etc. So what exactly this is and what is the significance? Just try to understand this. When we think of L1, that why did we send Aditya L1 to L1? So L1, if you see, if you notice the diagram, you'll see that L1 is a point which is directly on the straight line that is joining the sun and the earth. Correct? It lies on that straight line that joins the sun and the earth. And if there is anything that lies on this particular point, it will have a constant access to the sun, right? Because it lies in front of the earth, so it will always have an access to the sun. So it's not like a normal orbit that goes behind the earth and comes in front of the earth and goes behind the earth and so on. This is a point that will remain static, which will remain on the same straight line that joins the sun and the earth. So that's why this is a point that will have a constant access to the sun. This will never be behind the earth, it will never have any problem having the access to the sun. So that's why Aditya L1 is being sent to L1. Because what is Aditya L1? Aditya L1 is a mission that is going to uh, get us some information about the sun, right? It is going to study the sun, study the atmosphere of the sun, understand what the sun is like, understand the nuances of the atmosphere of the sun, and then send us back all the data with regards to the same. So that is basically how uh, L1 becomes crucial, and that is why we are sending Aditya L1 to L1. So Aditya L1 is being sent to L1 because L1 has a constant access to the sun without any hindrance. So that's the reason why we have sent Aditya L1 to L1 point. Then after that, James Webb Space Telescope is located at L2. Now, what is the significance of L2? If you see this, L2 lies behind the earth. Now, because it lies behind the earth, it will never be a point which comes in the front of the earth. So that's why this is a point that will be shielded from the sun. The rays of the sun, the radiations, the harmful radiations of the sun will never reach L2. So whether the X-rays or the ultraviolet light or the infrared rays or any kind of light or any kind of electromagnetic radiation, all these things will never reach L2 because you have the earth that blocks it. So you have the sun here, you have the earth here. So this is something that is blocking all the radiations that are coming from the sun. And L2 lies behind, right? L2 lies behind. So that's why all the rays, all the radiations coming from the sun, they will never reach L2. So that's why L2 becomes a very crucial point for us. How does it become important? Whenever you want to shield something from the sun. And James Webb Space Telescope obviously is a telescope. correct? So it has very sensitive mirrors and lenses, and these mirrors and lenses, they can lose their properties, they might malfunction if the radiations of the sun, they come in their way. So that's why we want to protect them. That's why we want to protect this uh, telescope from all these radiations. That's why L2 was chosen. All right, that's why L2 point was chosen, so that we can keep it safe. So James Webb Space Telescope has been kept at L2 because L2 lies in the shadow of the Earth, and thus the radiations of the sun can't reach L2. All right, so this is basically what we see. So that is why L2 has been chosen for James Webb Space Telescope. Now, when it comes to L4 and L5, these are 2 points that lie at 60 degrees, 60 degrees ahead of the Earth and 60 degrees behind the Earth. All right, 60 degrees ahead of the Earth and behind is on the same straight line where you have L1 and L2, but L3 lies behind the sun. All right, L3 lies behind the sun. So now in this case, L4 and L5, these are 2 points which are also said to be very stable points. All right, these are also said to be very stable points as compared to L1, L2 or L3. We see that L4 and L5 are way more stable, and that is why sometimes what happens is that a random asteroid might just lose its way, and if they come to L4 or L5, they get stuck there. They can get stuck there, and that is what has happened. There are two asteroids that we have discovered. Sorry. There are two asteroids that we have discovered, both at L4, and they are estimated that they would remain at L4 for like 10,000 years. For the next 10,000 years, this is their home, because L4 and L5 are very stable points, and that's why once something comes here, they can get stuck there for a while. And that is what has happened with these two asteroids, and that's why the name given to these asteroids is Trojan asteroids. That's why we call them as Trojan asteroids, because they have, in a manner, they have infiltrated the orbit of the Earth, and that's why the name Trojan has been given to these asteroids. So that's why in a manner they become constant companions for us. These are asteroids that become constant companions for us, because they get stuck at L4, and that's why they will also keep on revolving around the sun along with the Earth. So as the Earth revolves, similarly L4 and L5 points also will keep on revolving. So this is how we look at all these. Now even for L4 and L5, there has been a mission that was launched once, called as the stereo mission. The stereo mission was launched to L4 and L5, and this was basically to study the structure of the sun, or study the shape of the sun. To study the shape of the sun, this stereo mission was launched, and there were two sets of satellites, one kept at L4, one kept at L5, to do the three-dimensional analysis of the shape of the sun. So in this manner, even at L4 and L5, there have been certain missions that have been launched. Now L3 is the only point where I would say that there's nothing that we have launched, and we are not interested in launching anything to L3, because just imagine L3 lies behind the sun. Just imagine there's a very giant ball of gas that lies between the Earth and L3. So communicating with L3 for us is almost impossible. Just imagine the kind of uh, shape, I mean the kind of celestial body the sun is, the massive celestial body that it is. So for us to communicate something that is behind the sun is almost impossible, and that's why L3 is not a point that we really use, or it's not a point that we look forward to. All right, so that's why L3 does not really find any significance for us. The only significance could be if you are an alien, then you can just go there and keep your spaceship there. Nobody from the Earth will be able to detect you, and if you want to attack the Earth, then be at L3 and attack the Earth from there. but I'm very sure that nobody in the class is interested in doing that. So this is basically what we know about the Lagrange points. Basically, we are saying that this is these Lagrange points that we have, they are basically being created because of the gravitational pull. Gravitational pull. So we know that there are two bodies. You have the Earth, you have the Sun, and both of them are pulling these points. So that is where basically how we see that these points are created. And there is a basic, you will see that there is a mathematical calculation to how exactly we create, I mean, how exactly we detect where exactly these Lagrange points lie. So it's not that it's an observation, it's a simple calculation. It's not really a simple calculation. It is it is a mathematical calculation that we do, and we look into the gravitational effects of these two celestial bodies, and we calculate where exactly these Lagrange points could be situated. And that calculation is completely out of the scope of our discussion. If you are interested, just go and Google it, and you'll understand why I'm not teaching you how exactly the calculations are done. Right? So, but remember that the pull of the gravitational force is the most important one, is the most important point why exactly it is created. So just couple of days back you might have heard that Aditya L1 has sent its first pictures. Have you heard of this? It has sent its first pictures. Did you come across this news? Just I think 3-4 days back, I think it was in the news. Have you seen the pictures? Do you want to see the pictures? You'll be very happy to see the pictures. This is the picture. This is the this is the picture that has been captured. So if at all you were looking for those pictures, this right in front of you is the picture that has been, this is the first glimpse of the solar flare. So this first glimpse of the solar flare basically has been captured with the help of Helios or Hel 1 OS. So this is high energy L1 uh, optical. I'm not sure what the full form is. So we see that with the help of this, these are X-ray images that have been captured. So this is the X-ray image that has been captured by them. So this basically, I mean, these are just spectrometry analysis, and that's why these are looking like waves and not a real picture that you might have thought that you're going to get. So this is basically what we see, and that's why all these Lagrange points, they will specially become important for the examination, I believe, in the coming year, because they are constantly in the news. Yes, Garvit, you are right. This is high energy L1 orbiting X-ray spectrometer. So this is what the full form is, and this is the first picture that has been, or rather, the first spectrometric analysis that they have sent. So these are the Lagrange points. So Lagrange points position in space where gravitational forces of two body system like the sun and the earth produce enhanced regions of attraction and repulsion, and this is how these 5 points are produced. There are some points L1, L2 and L3 which are said to be unstable points, and then after that there are 2 points which are said to be stable points that are labeled as L4 and L5. So Lagrange points constantly has been used. There is another piece of news. There is something called as the Lucy mission. There's the Lucy mission that has been launched, and this Lucy mission basically is going to uh, capture Trojan asteroids. It is going to study the Trojan asteroids of Jupiter. Trojan asteroids of Jupiter. So that is basically, we see that constantly one way or the other, we see that all these points have been in the news. Now, one last kind of orbit is GTO, and this basically stands for geosynchronous transfer orbit. Geosynchronous transfer orbit. So now this kind of an orbit is an orbit which is often used whenever we are trying to launch any satellite to the high Earth orbit. Just know this, all right? Any rocket that we are using, or any launch vehicle that we are using, whether it's a PSLV or a GSLV or whatever kind of launch vehicle it is, the launch vehicles, they do not have uh, the capacity to go beyond 2000 or 2500 kilometers or beyond that. All right, they'll be able to go up to that. So up to 35,000 or up to 35,786 kilometers, they can't go. They can't carry the satellite up to that point. So what they do is that they will take the satellite as far as they can, which is just about 2000, 3000 kilometers, and from there on they use a certain uh, type of orbit which is called as the geosynchronous transfer orbit. So they will come until this point, and from here on they will again provide a thrust to uh, this particular satellite, and then we see that this satellite will keep on increasing its orbital altitude. So if you, for example, even if you have observed Chandrayaan 3 and if you have seen the path of Chandrayaan 3, you'll see that it is something like this, that let's say if you have the earth like this and you have the moon here, then in that case you'll see that it goes like this. It goes like this, and there will be a point where it will change its orbit and it will go like this. All right, so something like this is done. So these kind of orbits, these are called as transfer orbits, and there are multiple types of transfer orbits. There is Hoffman transfer orbit, geosynchronous transfer orbit. There is something called as gravitational slingshot. Sometimes it is called as gravitational slingshot, or also sometimes called as gravity assist. So there are multiple ways in which these kind of things are done. Uh, Sometimes with extra fuel, sometimes we see that it can be done with the help of this gravitational pull of another celestial body. So there are multiple ways in which it is done. So all these are called as transfer orbits, and one of the most common ones among the transfer orbits is the geosynchronous transfer orbit. All right, geosynchronous transfer orbit. So geosynchronous transfer orbit basically will take the satellite from the low altitude orbit or the low earth orbit to a high earth orbit. So that is basically, that is why we'll see that the apogee will lie at almost 36,000 kilometers. And if you want to know about the perigee, the perigee will lie at around 2000 kilometers. So perigee, basically this the closest point to this to the earth is called as perigee, and the farthest point is called as the apogee. So that is how basically this will be designed, so that it can just transfer the orbit or transfer the satellite from the low earth orbit to the high earth orbit. So what exactly will be done, that, and when I'm just writing it here, when exactly do we use geotransfer orbit? Launchers have the capacity to only go up to the low earth orbit for launching a satellite to the high earth orbit. We need the mechanism of GTO transfer the satellite from the low Earth orbit to the high Earth orbit. All right. So that is where the mechanism of geosynchronous transfer orbit will be used. Right. So this is about all these orbits. Now I have a special question for you. I had told you that there is a KBC question that has come from the PPT, and this was a question that was asked for 25 lakhs. Read the question. I'm launching the poll. If you have read the PPT, if you have given the correct answer, that's great. Have come down to 3 lakhs 20,000, I think it is, right? So, so correct answer is black hole. Sagittarius A star. Sagittarius A star basically is located at the center of our Milky Way galaxy, and it was in the news last year. It was in the news last year because the first images were taken. First images were taken in 2022. So that is why, that is basically why probably they would have asked this question. So it was a 25 lakh question, mind you, right? So only 54% of you win this money, and please don't ask me, go and ask Sony television channel to give you this money. Okay, so now we have our next topic, and the next topic is launchers. So until now we have basically discussed that we launch the satellite, we use the satellite for various purposes: Earth observation, navigation, satellite communication, experimental purposes. We discussed about the small satellites, the nano satellites, etc. And we discussed that we launch the satellite. There is something called as a PSLV or GSLV or SSLV that we use to launch these satellites. So this is basically what we are going to study in this part of our discussion about what exactly are we doing by these launchers. What are these launchers? So launcher obviously, as the name suggests, will launch. So that's why the name is launcher. So this will launch what we launch satellite or payload. Now when it comes to these launchers, there are three brackets into which we divide all the launchers that India has had until now. First, the retired launchers or the historic ones we used to use in the past. Now we don't use them anymore. Then after that, we have the operational ones that we are using today. So we have GSLV, GSLV, some rockets, SSLV, GSLV Mark 3. All these are the ones that we are using today. And then there are the ones which are under development or the future, where we have reusable launch vehicles, scramjet engine, or the next generation launch vehicle. Now these are the launchers that we have. These are the launchers that we have had, we have, or we are going to have in the coming future. So let's try to understand these. Not all of them are important, but some of them are really important for us. So first we start from the historic ones. So historic ones are the ones that we don't use now. We use them, and in a manner you can say that these are launchers that have very good stepping stones for us. This is where we began from, and then after that we have kept on building upon it, and better technologies, advancements in technology, we saw that we had better launchers later. So the first one was the SSLV or satellite launch vehicle. That's what SSLV. And the first operational version was SSLV, satellite launch vehicle 3. Now in this scenario, SSLV basically was, you can say, India's first experimental launcher, because this was a very small launcher. It did not have the capacity to launch the big bulky satellites that we launch today. So for example, it have launched only up to 40 kg large payloads, only up to 40 kg. Now at that point of time, we did not have any nano satellites, etc. Nano satellite is a very recent concept. You see that nano satellites, most of the nano satellites have been launched in the last 10 years. So for 40 kg, when it is 40 kg, you cannot say that we could have used it to launch landsats. No, because there was no landsat like back then. So a 40 kg class of payload is what we have launched. Then after that, we upgraded to ASLV, which was augmented satellite launch vehicle. Augmented. ASLV stands for augmented satellite launch vehicle. This had the updated capacity was up to 150 kg, and which would go up to 400 kilometers orbit. So this is the second launcher that we had. So first one was SLV, and the second one was ASLV. So these two are the launchers that the first two launchers for India, and both of them you can see in a manner where experimental launchers as well, because practical launch is not happening done with the help of these launchers. But then we come to the ones which are operational today, where the first name is of sounding rockets. So have you heard of sounding rockets? Do you know what sounding rockets are? Because I'm sure that you heard of PSLV or GSLV, because those things are in the news. But sounding rockets are not really in the news. But if you see, there are a total of 200 launches that have been done. More than 200 launches of sounding rockets have been done by India now. So it might be even surprising for many of you that something that you have never heard of has actually completed 200 launches. So 200 launches mainly because see when we say sounding, the meaning of sounding is to experiment or test. Right. So that's where the name sounding does not have anything to do with sound or something. To sound something is to experiment, to test. So that's where the name sounding rocket has been given to this kind of a rocket. So these are basically used for testing or studying something for testing, something for experiments. So whether it is related to weather-related experiments, climate-related experiments, defense-related experiments, sometimes testing out certain components that we are about to launch in a upcoming mission. So for all these purposes, sounding rockets can be used because these are smaller rockets. They are easy. You can construct, not take a lot of time, and also it's very low in cost. But they do not have a capacity that they can go very far. Most of them they can only reach the upper part of the atmosphere and nothing beyond that. So that's why we see that these are called as operations. These are called as sounding rockets because they'll be used for for experiments or tests. So that's why last year we saw that we basically have certain record that not really record, but there are more than 200 launches that now we have done. So why not hear about these launches? Because most of these are insignificant launches because some kind of only testing is etc. is done, and many of these are also defense-related tests which the government does not disclose that some kind of test has happened. So that's why many times do not even come to know that kind of launches actually took place. Now coming to a very important launch vehicle, something that can actually be reported for the examination, and this is polar satellite launch vehicle or PSLV. Now, PSLV stands for polar satellite launch vehicle. Polar because largely will be launching the satellites in polar orbits and the PSLV because that is used largely for the lower Earth orbit. They are largely used for the lower Earth orbit, and that is the reason why polar satellite launch vehicle. Because if you remember, because there's this yesterday that lower orbits are polar orbits, whether they're polar or synchronous orbits, both of them are polar orbits, and that's why launch vehicle that we are using for the lower orbit has been named as polar satellite launch vehicle. Now does that mean that we cannot launch anything else? We cannot launch anything that is going beyond Earth orbit? The answer is no. We can use it for other purposes as well. As long as you have a lightweight satellite, as long as you have a satellite which weighs less than 1500 kg, then that we can make the use of polar satellite launch vehicle. That's right. Even for launching the L1, we have used polar satellite launch vehicle or PSLV. And PSLV, that's why PSLV has been very crucial for India's success in the space sector. Now, when it comes to PSLV, there was a very controversial cartoon that was published, and this was a cartoon that was published in the New York Times. It was published in the New York Times in 2014, and this was the time of Mongolian mission. This was the time of Mongolian mission, the Mars Orbital mission, and that is the time when SOS was basically this is a cartoon that was published by so-called one of the biggest media houses in the world, the New York Times. Now, what they basically showing is you see that there is an elite space club, and there is a person coming with a cow, which represents India. So this is how the West works. This is a pure case of racism. This is how they generalize us that if you have to show an Indian, show the person with a cow. So that is what an Indian is, and should not be wearing good clothes, or let's not say good clothes, westernized clothes. So all these is basically how they are showing that there is an elite club, space club, which India is trying to enter, just knocking at the door. So it also basically created a lot of controversy. Obviously, I should have. And then also they apologized for it. Later on, they said that was they should not have religion and all that. But do you think that why they did not know what they're doing? It's just that this is the lens through which they look at us, or look at, let's say, Asian countries, African countries, whether it is India or other South Asian countries or African countries, or even China or Japan for that reason. You can always say that, you'll always see that this has been their approach. That they always have had an anti Asia or anti Africa kind of a stance, because they can't see that these countries are also rising, and these countries are also reaching the technological advancements that the West has achieved. So, and that's why whenever these kind of things happen, all the kinds of controversies happen. So for example, at the time of the launch of Mangalyaan mission, they were also saying that why does India have to even launch a Mars mission? India does not even have enough money to feed its population. So it does not have enough money to feed its population. So first they should feed their population, and then think of coming to space and launching a space vehicle. So these are the kinds of things that they say. So we also have to understand that this is a stance that they'll always take, because they cannot see us rising, or taking the same seat as they have been, in their words, basically. And that's why a wonderful reply was actually given by the Times of India. This was basically a cartoon that was published in the Times of India, where they basically they showed that now India is the elite space club, and there are others which are coming and knocking the doors and asking India to launch their satellites. And this basically happened when the launch of PSLV C-37 happened, because PSLV C-37 created a record. The record was that it took 104 satellites into space. 104 satellites into space in one single launch. Out of these 104 satellites, 95 satellites were US based. 95 satellites were US based. Only there were just three Indian satellites. Just three Indian satellites and 101 foreign satellites. Now, this also shows the importance of PSLV, because PSLV has been largely successful. For 10 years, between 2007 to 2017, there are almost 40 launches that were done by PSLV, and none of them failed. All of the 40 odd launches were successful, which is a very big achievement for any space agency. There's no space agency that can say that they have had 40 consecutive launches over a period of 10 years without having a single failure. So that shows the importance of PSLV. And because of that, we saw that a lot of international projects also started knocking the doors of India, knocking the doors of ISRO. And ISRO started launching a lot of foreign satellites as well. So because of the success that PSLV has shown, not only that, the launch cost of PSLV is very, very low. All right, it's very, very low. compared to many of the launches that are done by US based space agencies or European Space Agency and so on, you'll see that compared to them, PSLV launch takes a lot lesser cost. For example, there was a cost analysis that was done between Ariane 5 of France and PSLV. So one Ariane 5 launch almost takes $100 million. It takes almost $100 million, whereas one PSLV launch costs almost $15 million. That's the kind of difference that we are talking about, and that's the reason why so many launches have been coming to PSLV, coming to ISRO, because first of all, we are successful, we are highly successful, and we are very cheap compared to any other space agency. And that's the reason why we see that there are so many projects that come in the way of India. So much so that PSLV has been named as the workhorse of ISRO. It has been named as the workhorse of ISRO. So that's why we have seen that there are so many things. I mean, if you go and do the analysis of cost of the Mangalyaan mission, the per kilometer cost of Mangalyaan mission is lesser than what you probably pay to an auto per kilometer in your city. I mean, if you're not taking a shared auto, that is. So then in that case, uh, Mangalyaan, if you travel from one place to another in a city like Bangalore or Delhi, you probably are paying lesser if you were traveling through Mangalyaan instead of traveling through an auto. So that's why we see that why PSLV has taken such a center stage. That's not, although it's called as polar satellite launch vehicle, but it's not that it only launches satellites to the low Earth orbits. It also launches satellites to other orbits if required, if these are lightweight satellites. So that's why Mangalyaan mission was launched with the help of this. Aditya L1 mission very recently was launched with the help of this. Chandrayaan 1 mission was launched with the help of this. All the IRNSS satellites that we discussed, all of them were launched with the help of PSLV. The Astrosat mission was also launched with the help of PSLV. So all these missions, even though they are not polar missions, even though they are not going to the low Earth orbit, still we have used uh, the services of PSLV for all of these launches, and largely because of the stability that we see with PSLV. That's the most important reason there. Right. So when it comes to PSLV, we see that PSLV has 4 stages, alternately using solid and liquid propulsion systems. Now, how exactly it is arranged, just try to understand this once. That we have the first stage where we have something called as hydroxyl terminated polybutadiene. You don't need to remember the name. HTPB, if you remember, that's more than enough. This is basically the solid stage. This is the solid stage. Now, when we say stage basically means, in simple terms, you can say we are talking about compartment of fuels. It simply means fuel compartments. All right. So these fuel compartments are called as stages. So there is a solid compartment, basically having the solid fuel. Then above that there will be liquid compartment, the second stage, then again solid stage, then again liquid stage. This is how the arrangement is. So second stage, basically this is where we have the Vikas engine, cause it carries the liquid propellant called as unsymmetrical dimethyl hydrazine, or UDMH. Again, as I told you, no need to remember the name, only UDMH. If you remember, that's more than enough. You don't need unsymmetrical dimethyl hydrazine. Then after that, the third stage again is HTPB, which, so first stage is solid, the second stage is liquid, the third stage again is a solid stage, and the fourth stage again is a liquid stage. So this is how the arrangement is. All right, this is how the arrangement is. That if, let's say, I show you a basic line diagram, this is how it is. That you have a solid stage, then a liquid stage, then another solid stage, then another liquid stage. This is the part where you have the payload. This is the part where you have the payload, or in other words, you can say the satellite. This is where you have the satellite. Right. So, and this part is called as the core, or sometimes as the base of the launch vehicle. So this is basically how we have a basic arrangement of the PSLV. All right. Now, when it comes to PSLV, there have been various variants of PSLVs that we have used all this while. Among all these, the most important one I would say is PSLV XL. If you see this, PSLV XL. Once we started using PSLV XL, this was the first instance when PSLV XL was used, and this was during the launch of the first Chandrayaan mission. This was Chandrayaan 1 back in 2008. This was back in 2008, and this time if you see, this is basically Aditya L1. So the latest PSLV launch has been Aditya L1, and the first one was Chandrayaan 1. Now when we say PSLV XL, the name has been given basically. When you say XL, something is XL, you basically mean extra large. Same is the case here as well, that this is the launch vehicle which is the heaviest launch vehicle, so it has a capacity better than the other variants of PSLV. Because something like a PSLV CA, you don't need to know this, I'm just telling you. PSLV CA, for example, is the lightest variant. It cannot carry more than 1000 to 1200 kg of satellites. Above that, in most of the cases, PSLV XL will be used. So all the heavy launches can only be done with the help of PSLV XL. So that's it. These are all these launchers, the different types of launchers that we have, out of which, as I told you, this is the most important one. This is the one that is used for most of the bulkier launchers that we do. Then after that, we have the geosynchronous satellite launch vehicle, or GSLV. Now GSLV, the name has geosynchronous, meaning that largely we'll be using it for the high Earth orbit. But apart from high Earth orbit, if there are other heavy launches that we are trying to do, then in those cases also GSLV will be used. So for example, the upcoming Gaganyaan mission. Whenever the Gaganyaan mission is launched, the Gaganyaan mission will be launched with the help of GSLV. Even though you are not going to the high Earth orbit, all right? You're not going to the high Earth orbit because, for example, Chandrayaan 3 also was launched with GSLV. Chandrayaan 2 also was launched with GSLV, but they are going beyond the high Earth orbit, right? They're going to the moon. But in this particular case, Gaganyaan mission, even though it is going to go to the low Earth orbit, even then geosynchronous satellite launch vehicle is being used because it's a very heavy launch. It's a very heavy launch, and that's why we needed the services of geosynchronous satellite launch vehicle. So that's why just remember that whenever you have lightweight launches, we use PSLV. Whenever we have heavyweight launches, we use GSLV. Largely, you can say more or less 1500 minus is PSLV, 1500 plus is GSLV. So this is how we do it. Now, when it comes to GSLV, the structure, the design is a little different. This time you have 3 stages. All right. This time you have 3 stages. Again, the base and the payloads are the same. This is where you have the payload. This is where you have the base. Now, in this particular scenario, there are 3 stages. The first one again is solid, same as what we saw with PSLV. Second one again is liquid, but this time the third stage is a cryogenic stage. The third stage is called as the cryogenic stage. So a basic difference between PSLV and GSLV is what? PSLV has solid, liquid, and in case of GSLV, it is solid, liquid, and cryogenic. Now, when we say cryogenic, right? When we say cryogenic, cryogenic means what? Do you know the meaning of the word cryo? Do you know what we mean by cryo? Cold, low temperature, frozen, correct. So basically, whenever there is any technology that works at very, very low temperature, all right? So that's why I'm writing here extremely low temperature. So any technology that works at extremely low temperature, we say that it's cryogenic. So in case of the fuel that we are using here, this also is called as cryogenic mainly because of this fact that here the combination that we are using is a combination of liquid hydrogen and liquid oxygen. And to liquefy hydrogen, you need to go to minus 250 degrees Celsius. Then only you can liquefy hydrogen. And even for liquefying oxygen, you need to go to minus 150 degrees Celsius. Then only you can liquefy oxygen. So that's why this fuel is called as a cryogenic fuel, because it is a fuel that works at extremely low temperature. Now, when it comes to this cryogenic fuel has been very important, and strategically it has been very important for India, because this is something that has helped us in getting uh, us ready for the GSLV. And cryogenic fuel is not a fuel which is very easily available. It's not a fuel that everybody has an access to. There are only a handful of countries in the world which have an access to cryogenic fuel, which know how to use cryogenic fuel and how to produce cryogenic fuel. So that's why this was a very special uh, it was a very special moment for India, when we also were able to produce our own, or we were able to uh, get our own cryogenic, or rather create our own cryogenic fuel. So that's why it became very crucial from that perspective, where for the first time India also started using cryogenic engine or cryogenic fuel. So for example, if I just name the countries right now, there are only a handful of countries, as I told you. So uh, the US has it, the European Union has it. So although it has been produced by France, France was the first country, but European Union has it. So that's why European Space Agency also has it. So that's why I'm writing European Union. Then apart from that, you also have Russia, you have China, and you have Japan. These are only countries, of course, apart from India. These are the only countries which have cryogenic fuel. These are the only countries that have cryogenic fuel. Otherwise, they don't. Nobody else has. And creating cryogenic fuel, working with cryogenic fuel is extremely difficult. For us also, it has taken a lot of time for us to master this cryogenic fuel. For example, first time we tried cryogenic fuel in 2001. We were working on cryogenic fuel and we succeeded in 2001. But if you look at the GSLV launches that have happened between 2001 to until 2010-11, you'll find that more than 50% of them failed. And this was largely because of the instability of cryogenic fuel. We were not able to control that cryogenic fuel, and that's why we saw that there were a lot of launches that kept on failing. But then after that, we have been able to improve upon them, and then we see that 2011 or beyond, there is no failure with GSLV after 2011. But until 2011, you'll see that there have been a lot of failures, and largely they are attributed to the failure of cryogenic and we not being able to control the cryogenic fuel. So, that's why just remember that cryogenic becomes very crucial in the working of the GSLV. So as we know that GSLV is something that we use largely for communication satellites, right? Largely for communication satellites that are going to the high Earth orbit, but also heavier satellites. Anything generally more than 1500 kg is where we will try to use the services of GSLV. Now, in case of GSLV, we have seen that there have been three variants of GSLV: GSLV Mark 1, Mark 2, and Mark 3. Now, GSLV Mark 1 and Mark 2, if you look at the chart, and again, this chart is not important for your examination, it is just for information that I'm giving you. If you see this, they are very similar, right? They are very similar. Height is same, lift off mass almost the same, number of stages the same. The payload that they can carry to the low Earth orbit is the same. The payload that they can carry to the geosynchronous transfer orbit is also the same. But then came GSLV Mark 3. Now this GSLV Mark 3, if you see, the data is very different. That it can carry up to 8,000 kg to the low Earth orbit and up to 4,000 kg to the high Earth orbit. So that's why it is seen as the next generation of GSLV. Although what we have seen is that lately it is also called as LVM3. ISRO scientists, they have started calling it as LVM3, meaning Launch Vehicle Mark 3. Right, Launch Vehicle Mark 3. So that is why this name, they say that because it's very different from the versions of GSLV Mark 1 and Mark 2, so it's not wise to name it as GSLV Mark 3, is basically what they have been saying. And off late you will see that everywhere whenever the launches happen, LVM3 is used instead of calling it as GSLV Mark 3. So just remember that GSLV Mark 3 and LVM3, they are both the same, just that they're both the same, just that the nomenclature is different. Technologically, they are not. Technologically, they are same, just the different names are being used for GSLV Mark 3 now. So that is basically how we see that. So basically, Mark, when we say Mark, is generation, in a manner, generation. So Mark 1 is the first generation, Mark 2 is the second generation, and then Mark 3 is the third generation of launch vehicles that we have now. So in this manner, we see that GSLV is basically, this is how GSLV has been progressing all this while. And it has taken a lot of effort. It has not been an easy task for India to get hold of the cryogenic fuel, because it was 1970s itself for the first time when we could have gotten uh, the cryogenic technology from France. But at that point of time, because of various reasons, we could not. Uh, so 1970s we could not. Then I think it was 1986 when there was a US based company that was ready to give India cryogenic technology, but at a very high price. So that's why India again had to refuse. India said that we cannot spend so much of money in just getting this technology. So first we could not get from France. Then secondly we could not get from US because of the price issues. Then after that, as always, USSR came, and this was almost the time of USSR getting disintegrated into Russia and other countries. And Russia was ready to give cryogenic technology to India for free, not charging anything. And a couple of engines had even come to India. And this is where US intervened. And US did not let the technology transfer happen. As always, I mean, US could not see that technology transfer happen, because then India would also have become one of those elite countries that have the cryogenic technology, and did not let it happen because there is something called as MTCR. If you know this, this is Missile Technology Control Regime. And uh, India was not a part of MTCR back then. Now India is a part of MTCR. But US and Russia, both of them were a part of MTCR. India was not a part of MTCR. And according to the laws of MTCR, uh, an MTCR country is not allowed to give a missile technology to a non-MTCR country. So Russia was an MTCR country, India was a non-MTCR country, and this is a missile technology. I mean, you'll see that even during World War II, cryogenic technology was actually being used by France and some other countries. So it counts as a defense technology, counts as a missile technology. So that's why under the laws of MTCR, Russia was not allowed to give it to India, and US intervened there. US said that I'm going to put sanctions on both these countries if they let this transfer happen, and hence both the countries backed out, and the technology transfer could not happen back in uh, it was, I think, 1989. But then India started working on its own cryogenic technology, and then next 10-12 years, we got it. It's also said that behind the scenes, Russia was still helping India, but we'll never know whether this was happening or not happening, because this is not an official news. India never said that we are getting the help from Russia. Russia did not say that we are helping India, but it is said that probably Russia helped India in the coming years to in developing this technology on our own. So ultimately, we see that this has been a big technology for India. All right, look at this question. No, no, Wonderful. So 68% of you have marked A, which is absolutely correct answer. Let me just discuss this for the rest of you. With reference to India's satellite launch vehicle, consider the following statements. First statement says PSLVs launch the satellites useful for Earth resource monitoring. This is correct. We discussed that remote sensing satellites or Earth observation satellites is what PSLVs launch. So this is what it is. That's correct. GSLVs are designed mainly to launch communication satellites. This is also fine. This is correct. So first statement is good. Second statement is satellites launched by PSLV appear to remain permanently fixed. Permanently fixed in the same position in the sky as viewed from a particular location on the Earth. If you remember, what we discussed is that when you are in the low Earth orbit, the orbital period is of just 1.5 to 2 hours, correct? So it cannot be permanently fixed. We discussed that it appears once in a day, right? This is what we had discussed yesterday, once in a day. In case of the ones that are being launched by GSLV, if you remember, at 35,786 kilometers, the orbital period is of 24 hours. Correct? It is of 24 hours. So what do 24 hours mean? That's the rotational period as well. Correct? That's the rotational period of the Earth. So as the Earth rotates, that is how the satellite also revolves around the Earth. So that's why it remains permanently fixed with regards to a point on the Earth. So that's why the ones that will be launched by GSLV, the communication satellites that we will be launching with the help of GSLVs, especially the ones that are being launched to the geostationary orbit. The geostationary Earth orbit, that's why geostationary. Stationary with regards to the Earth. That's why geostationary. So it will be the one that is permanently fixed. So that's why this is wrong. Because this will be GSLV, correct? So that's wrong. Third statement is GSLV Mark III is a four-stage launch vehicle with the first and the third stages using solid rocket motors and the second and the fourth using liquid. This is what? What is this? Is this GSLV or it is something else? Yes, it is PSLV. Perfect. This is PSLV. So that's why this is wrong. So correct answer will be A. One only. Then another small topic but significant has been the Vikas engine. Now, Vikas engine is an engine that we use for the liquid propulsion systems. Alright, for liquid propulsion systems. So, liquid propulsion systems are very difficult to control. They are very difficult to control, and that is where we have been able to pioneer. This is an engine that basically we got from a licensed version of the Viking engine, and this Viking engine belongs to France. In a manner, we adopted it from France. We took the license from France, and we developed it into the Vikas engine. Have you seen that film, Rocketry? Also won the national prize this year. If you've seen the film, they've shown it, that how we were able to actually uh, make it our own and how we were able to stabilize Vikas engine even better than. There's a scene in the film where they show how they were able to make Vikas engine even better than the Viking engine. They were able to stabilize it even better. Yes, Dr. Nambi Narayanan. It's based on his life, right? So they've seen it, they've shown it in the film also. So how we took Viking engine and we actually were able to build Vikas engine, taking the license from there. And today, and it's not something which has been just dramatized in the film. Today, Vikas engine is said to be one of the best variants of liquid propulsion systems in the world, better than the Viking engine. Actually, better than the Viking engine. So we use Vikas engine for the liquid propulsion, whether in GSLVs or PSLVs. We know that the second and the fourth stages of PSLVs is the Vikas engine, and in the second stage of GSLV also it is the Vikas engine. So we use Vikas engine wherever we have the use of liquid propulsion system. Then after that, one more launch vehicle that we have just added to our arsenal has been the small satellite launch vehicle. Now, in case of small satellite launch vehicle, of course, it will be used for the launches of the small satellites, largely the nano satellites. largely the nano satellites, and you can also say the micro satellites. Although numbers of micro satellites are pretty less compared to nano, but nano satellites and micro satellites will be launched largely with the help of the small satellite launch vehicle. Now, in case of small satellite launch vehicle, it's a three-stage solid propulsion stage. So all the three stages are solid stage, but still there is a small liquid stage towards the end, which is called as the velocity trimming module. Velocity trimming module is the one that is liquid. Velocity trimming module is the one that is liquid, and it is liquid. So just you have to understand this, that when it comes to the liquid stage is something which is very, very difficult to handle. So it has not been a very easy scenario for India to do it, and that's why. But liquid stage is also required whenever you want stability of the orbit. Solid stage. So just understand this, all right? You'll always see that the first stage in PSLV also we saw that the first stage was solid. In GSLV also we saw that the first stage was solid, and in SSLV also first stage is solid. So we'll see that in most of the cases, whenever a rocket is being launched, first stage is always solid. You know why? The reason is that the solid fuel provides more thrust, meaning more force. It provides more force, and in the first stage you are on the earth. So because you are on the earth, it means that it's going to take a lot of effort. It's going to take a lot of effort to launch a satellite from there, because the gravity is pulling. Correct? The gravity is pulling it towards the earth. So that's why solid is always used in the first stage. After that, the arrangement is based on whatever our requirements are. But largely you will see that the last stage will either be liquid or cryogenic, but not solid. The reason is that controlling solid is not easy. Controlling the solid stage is not easy. It just provides a lot of force, but controlling it is not easy. So that's why when we are near the orbit, then in that case we need a liquid stage or a cryogenic stage. So that's the reason why, even though it's a three-stage solid propulsion rocket, still there is a small velocity trimming module, which is a liquid fuel, which is easier to control. Just think of your daily life. Our vehicles, they run on petrol or diesel. So whenever you want, you can uh, let the flow of petrol or diesel happen into the engine, and it will be easy to control. On the bikes, etc., especially the older bikes, you would have seen that there is a fuel, uh, that small thing that you can help to control the fuel. You can switch it on, or you can get it on or off, and accordingly you can control the flow of the petrol or diesel. So that's not possible with, if let's say your fuel was coal. That if your motorcycle or if your scooter or car was running on coal, then in that case you can't control it, because once the combustion of coal has started, you cannot just stop or control the combustion of coal. So that's why we see that. I mean, just something that you can also draw from the daily life, and something at a larger scale that is used in the small satellite launch vehicle, or for any launch vehicle for that matter. Now, recently, launch vehicle, this SSLV also has been in the news for this reason, that ISRO basically might transfer the small satellite launch vehicle to the private sector. It will ask for bids, and there will be private companies which will be bidding for it, and the entire technology will be transferred to the private sector, and everything, basically the launch, the operations, the manufacturing, each and everything will be done by a private company. So that's something that ISRO is probably going to do, and that's why this was also in the news just a couple of months back. Now, coming to the future. So this is where we are right now with SSLV, PSLV, GSLV, etc. Coming to the future, there are things that have been tested, there are things that have been announced. So for example, the first one here is the scramjet engine. Now scramjet engine, when it comes to it, scramjet is a technology where we are using a form of air breathing jet engine. Air breathing jet engine. So scramjet stands for supersonic combustion ramjet. Stands for supersonic combustion ramjet engine. So this supersonic combustion ramjet or scramjet is something that will use the atmospheric oxygen. the oxygen that is present in the atmosphere as oxidizer. Now understand this. Why do we need scramjet? Or what is the advantage that scramjet is going to give us? So when it comes to the scramjet engine and when we are talking about the oxidizer, the role of oxidizer is to help in combustion. Oxidizer helps in combustion, any combustion. Even if you are trying to light a matchstick, even if you are trying to light a matchstick, the matchstick is able to start the combustion because there is oxygen in the atmosphere. Let's imagine that if there was no oxygen in the atmosphere, then combustion will not happen. I mean, we'll also die, that's another story, but combustion will not happen if there was no oxygen in the atmosphere. So that's why the oxidizer basically helps in combustion. So you need some kind of, either you need oxygen or you need something that can act as oxygen, act like oxygen. That's called as an oxidizer. So every launch vehicle carries a lot of oxidizer along with the solid fuel or the liquid fuel or the cryogenic fuel. You would have to carry a lot of oxidizer as well, so that it can help in the burning of the fuel, in the combustion of the fuel. So now what happens is, because of that, it takes a lot of space. It takes a lot of space in the launch vehicle. So with scramjet, what we want is that don't carry the oxidizer. Why not use the oxygen that we have in our atmosphere? So in that case, you'll be saving some space. The weight of the launch vehicle will come down. So you will be able to save the fuel as well. And you'll be able to carry more payload as well. All these things can be possible with the help of scramjet. And that is the reason why the scramjet engine has been tested. Now, testing has happened almost 6-7 years back, but we still are looking at the future. So, so when it comes to scramjet, so the advantage of scramjet will be that first of all, it will uh, save space, reduce the vehicle weight, reduce fuel consumption, and increase payload carrying capacity. Right. So this is basically why scramjet will be used. So scramjet has been tested once. So if you see this, this is how basically scramjet works. That if the engine or the vehicle is moving in forward direction like this, then there is an incoming air will come like that. Right. Like this is how the incoming air will come, and it will get compressed. The temperature of this air rises, and this is where it comes in contact with the fuel. So it comes in contact with the fuel, oxygen will help in the combustion, and hence the movement of this vehicle will keep on happening. Now, when it comes to this scramjet, it can operate at hypersonic speeds. Hypersonic speeds. So, so when it comes to hypersonic speeds, means that we are talking about speeds which are very, very high. So there are these terms that we use. Sorry, subsonic, supersonic, and hypersonic. So now if you see here, what we know is that hypersonic speed basically means that it will be able to travel at a very fast speed. There is something which is called as Mach. There's something called as Mach. So anything that is less than 1 Mach, subsonic is less than Mach 1 or 1 Mach. So 1 Mach basically is the speed of sound. Right? So or rather Mach 1, Mach 1 basically is the speed of sound. which is almost, you can say, 340 meters per second. So anything less than 1 Mach or Mach 1 will be called as subsonic. Anything that is between Mach 1 to 5, generally between 1 to 5, is called as supersonic, and anything that is greater than Mach 5, anything that is greater than Mach 5 will be called as hypersonic. So in this case, we are saying that it will be able to work at hypersonic speeds, which ramjet is not able to. Ramjet can work in supersonic speeds, but not at hypersonic speeds, but it can. And this technology, although it has been developed by ISRO for space vehicles, at the same time, it actually can also be used for missiles. Can also be used for missiles. For example, even the BrahMos missile that we are building, and that also scramjet technology will be used by DRDO. So a technology that has been developed for space vehicles by ISRO can also be used in defense technology. And we already see that we are building defense technology based. I mean, there are missiles that we have built, the hypersonic missiles that were in the news this year as well, plus all the BrahMos missile, the cruise missiles, they all will be using the scramjet. That's why scramjet technology becomes very crucial, not only from space technology perspective, but also from defense technology perspective. Then after that, we also have something called as reusable launch vehicle. Now again, this is something, a technology that has been tested by ISRO back in 2015. And then after that, we have been working on the version of reusable launch vehicle. So as the name tells you, this is a reusable launch vehicle, meaning that this is a launch vehicle that can be reused. That it's not expendable. Normal launch vehicles like PSLV or GSLV, etc., they are called as expendable launch vehicles. That they can be used only once. Right? They'll be destroyed and they will be used once. But this is a launch vehicle which, after being launched, it will fall back to the Bay of Bengal, and then it can be collected from there again, and it can be used again. So we have already tested this technology once, and this was back in 2015, and now we see that we have been building on or working on a version of it. Then there is another one that has been announced for the future, and this is the next generation launch vehicle. Now this next generation launch vehicle is supposed to replace all our operational launch vehicles. PSLVs or even the GSLVs, they will be replaced by this next generation launch vehicle, because it will be a three-stage reusable heavy lift launch vehicle that will have a capacity of up to 10 tons, up to 10 tons to GTO, meaning 10,000 kg. 10,000 kg to GTO. Right now, the GSLV Mark 3 with GSLV Mark 3, or what is also called as LVM3, we have a capacity of up to 4,000 kg to GTO. So this is something that is going to increase to 10,000 kg to GTO. There is something which is called as semi-cryogenic propulsion that they have also tested. Even this was in the news in the month of May, that semi-cryogenic propulsion was tested. This is basically where they mix kerosene in the cryogenic fuel. So that's why it becomes semi-cryogenic fuel. So in this manner, we see that it's going to be reusable, it is going to be a heavy lift vehicle, and it might become one single launch vehicle for India. For all our polar satellite launches, all our geosynchronous orbit launches, every launch can be taken care of this one single launch vehicle. So this is something that just has been announced. That's it. There is no word that is happening. There's nothing official that was said. Sorry. That's that there was a seminar last year where ISRO chairman was speaking, and this is where he had announced that this is something that ISRO is going to start working on. Now, lastly, about the fuel, as I told you, that there is a solid fuel, liquid fuel, cryogenic fuel, and so on. So the solid fuel is called as HTPB, This is something that we are using where we are using the first and the third stages. First and third stages of the PSLV launch vehicle. In the first stage of the GSLV launch vehicle, and all three stages, of SSLV. Then after that you have UDMH, that is unsymmetrical dimethyl hydrazine. This is used in the second stage. This is used in the second stage of both PSLV as GSLV. Then we have MMH, which is monomethyl hydrazine. This is used in the fourth stage of PSLV and the velocity trimming module of SSLV. Right? This is where MMH, which is a liquid fuel, is used. So this is solid rocket propellant, this is liquid, and this is again liquid. Then after that we have LOX and LH. LH stands for liquid hydrogen. Liquid hydrogen. So this is what? This is the cryogenic fuel. This is the cryogenic fuel, and LOX is liquid oxygen. So liquid form of oxygen, and this is basically the cryogenic oxidizer. This is the cryogenic oxidizer. And then lastly we have MON, which stands for mixed oxides of nitrogen, and these basically are the ones which are used as oxidizers. This mixture becomes the oxidizer both for solid and the liquid fuel. It's oxidizer for HTPB, for UDMH, and also for MMH. For all these, this becomes the oxidizer. So this is, I mean, just a factual part of it, nothing to explain, and don't really need to go into the detail of all these things. So this is about our first part. This is about all the space technology and everything. If you have any questions, please let me know. Anything if you want to ask. This is relatively unstable. I mean, compared to L4 and L5, L1, L2, and L3 are unstable points. But if you see in that sense, any normal orbit is even more unstable as compared to L1, L2, or L3. So then in that case, we can't launch any satellite. But when we say unstable here means in comparison to L4 and L5, it is unstable. Chandrayaan 3, as it requires more fuel and time. See, when it comes to the use of the orbital maneuver, basically it helps us also understand how the satellite is going, and even if, let's say, there are any corrections required, any changes required, it helps in getting all of that done. Detail do we need to remember about GSLV Mark 1, Mark 2, and Mark 3? Nothing really. Only the distance that they can cover. How much they, the amount of payload that they can carry. How much they can carry to low Earth orbit, and how much they can carry to high Earth orbit. That's it. Apart from that, nothing else is required. What we are saying is that they are relatively stable positions. So because they are stable, just imagine them like a plateau. That others are mountains and these are plateaus. So this is something that gets stuck there. It gets stuck there for a while. And that's why, if, let's say, there is any asteroid that is just maybe having its own path, if by chance it comes to L4 of any planet, not only the Earth, of any planet, it might get stuck there. So that is basically what happens. Lucy also the same. Why not scientists send launch vehicles to other planets except Earth, Mars, and Moon? It's difficult. It's very difficult. The first time that we tried actually was Venus. We started going to Mars later, the first launch that we had done for any planet was actually Venus. And as we came near Venus, this is where we realized the condition on Venus. We lost all the communication with the satellite that was sent within minutes, I think. And then after that, we realized that the conditions of Venus are not suitable for sending anything there. So then we chose Mars. Others don't even have a solid surface. I mean, sending something to Mercury has been done. Messenger is the name of the mission that we have sent to Mercury. Has been done. Jupiter, you cannot land. Saturn, you cannot land. These do not even have a solid surface. So that's why we have orbital missions there. For example, there was the Juno mission for Jupiter. So there have been all these missions. So it's not that we have not tried anywhere else. Of force. So that's why solid starts with. And then the position has been done in a manner that they can control the flight path of the entire system of PSLV and the velocity driven module of SSLV. Just know this much. Beyond that, nothing is required. So because you are not carrying the oxidizer, you save some space. Correct. So that's the first thing, because oxygen from outside is being used as the oxidizer. So that's why you don't need to give that space to the oxidizer. So you save some space there. Then you reduce the vehicle weight because you're not carrying the oxidizer. So weight reduces. We reduce the fuel consumption because higher the weight you are carrying, you need more energy and hence you need more fuel. So because the weight reduces, that's why you can say that even the fuel consumption also reduces. And it can increase the payload carrying capacity because weight reduction has happened, so more satellites can be carried. DMH and MMH. For using the liquid fuel, we need gas engine because normal engines, they do not function very well with liquid propulsion, and that is where this design was done. A lot of testing and experiments were done that finally we were able to develop our own gas engine. So gas engine, just one line about it, used for liquid propulsion. Sorry. When the first time Scramjet was tested, it was 2016 that we tested it. Advantage of cryogenic fuel. Cryogenic fuel basically has a better capacity. So it has a better capacity and a better efficiency. So that is the main reason why we want to use cryogenic engine. Points at average points. These are mathematically calculated points. So only 5 points actually get created. Very highly unstable technology. So it's not that easy to use. It's also very costly. So manufacturing cost is also very high. So Lagrange points are 5 special points that are generated because of the gravitational effects of a two-body system where one body is revolving around another body. So that's why between the sun and the earth there are these 5 points that are produced because of basically the gravitational effects of the sun and the earth. Hence transferring of the satellite from the low Earth orbit to the high Earth orbit. Scramjet can only be used for the first stage. We cannot use Scramjet for the higher stages because after that the oxygen will be very thin and we can't use that atmospheric oxygen. So we can only use the atmospheric oxygen in the lower part of the Earth's atmosphere near the Earth. Only for the first stage we can use it. Videos also that have been released about how the path of the satellite would be at L1. If you look at that path, you will understand that yes, it will constantly keep on moving along with the movement of the Earth. Launch vehicle and the cost of launch with LE5 is pretty high. That they are stable. Small scale is like it's a region, so it will just keep on revolving around that region. Is that enough? Not at all. That sometimes also makes it difficult for me to see the questions. And I'm going line by line with all the questions that I see here, and then I see that there are some of you who just asked the same question many times. So I'll come to your questions. Not that I'm not answering your questions. Poland, France has it, Japan has it, China, Russia, USA has it. So all these countries, they have this cryogenic technology. They have the capacity to go that far. Hardly 2,000 kilometers they can go. And the center of the Milky Way galaxy is billions of light years away. So it's not even possible for them to go there. Any different sensitivity value for other recent parts will be different. So basically, any will launch nothing like that. You can use it whenever you want. Not remote. Basically, those are the stages. So one by one, the stages will detach from the launch vehicle, and it makes it lighter and makes it easier for it to go further. So as the Earth revolves, the LP would also have to revolve, and LP is always on the other side. It or sometimes in ocean as well. Then feel long break. And revolution that it has, the time period of revolution is little more than the Earth. And that's why there will be a time when it will significantly keep on increasing and it will again get out of N4. Light, how you use the fuel. I mean, even if you are driving a car, you use your petrol or diesel, then only you are able to drive the car. Any work that you are doing, you need energy for it. And what is fuel? Fuel provides energy. So that is why you need it. It has been one of the best examples of how any science-based organization should work. And in India, it has led by example. And that's why we see that there are other areas of scientific advancement in India which also have been trying to follow the sort of what has happened in space technology. So overall, when it comes to the importance of ISRO, everything that we have done in space technology, it's all thanks to ISRO and thanks to the scientists who have worked over the last few odd years in ISRO. But first and foremost, when it comes to ISRO, we have to just note this one sentence, right? This just one sentence, the vision of ISRO, what exactly does ISRO do? So the vision is to harness space technology for national development while pursuing space science research and planetary exploration. Meaning that the primary function, primary purpose of ISRO is what it is for national development. And what do we mean by national development? Anything with regards to wherever people of India could be helped. And that is precisely what has happened. Whether it is agriculture, whether it is weather monitoring, whether it is resource monitoring, whether it is disaster management, whether it is communication, whether it is any other for example, even for defense purposes, even for navigation purposes, for each and everything, ISRO has launched satellites, and these satellites only help the people of India. So that has been the primary purpose, and that's why it says while pursuing space science research and planetary exploration, there have been more than hundreds of launches that we have done which are related in one way or the other with the people of India, and there are only a handful of launches that we have done which can be attributed to something like space technology. Like for example, Mangalyaan, Chandrayaan 1, 2, and 3, and Aditya L1 AstroSat. Only 6 missions, and there is a 7th upcoming Gaganyaan mission. Apart from that, all the other launches that we have done, they're all related to national development, or let's say help are going to help people of India in one way or the other. So that's why this vision is very important. Mission is nothing but the breakdown of everything that ISRO does. Not very important for you to know. Just that if you read it once, you understand what exactly it is. Now, in the important part, in understanding of ISRO is about the organizational structure of ISRO. When we look at the organizational structure, there are certain parts, certain units of ISRO that become important for you, because they have been doing the most important jobs whatever ISRO has to do, and these are the ones. All these that I have in this line, they become important. Apart from that, these two become important, and this one right here in space becomes important. These are the words that become important from the examination perspective. So now when we look at what exactly they do. So for everyone, just know even in one line what exactly they do. Right? So for example, the first one is Vikram Sarabhai Space Center, VLSC. Vikram Sarabhai Space Center. All the full forms are present here at the bottom of your screen. If you want, you can check that in your PDF. So Vikram Sarabhai Space Center. What is the role of Vikram Sarabhai Space Center? Basically works on launch vehicles. It works on launch vehicles and all the related technologies. So that is basically what is called as Vikram Sarabhai Space Center. What is the role of Vikram Sarabhai Space Center? Everything with regards to launch vehicles. Even the smallest of things, even the kind of paint that you will use on the launch vehicle, even that will be developed at Vikram Sarabhai Space Center. Then after that, you have liquid propulsion system center. Now this basically is used for fuel development. So primarily for the liquid propulsion system, but even the other fuels that they also coordinate with LPSC and they help in the development of your fuel. Then after that we have SDSC, that's a Satish Dhawan Space Center, which basically is where we launch our launch vehicles from. So that is basically where the launch pad is located. That is the launch base infrastructure for India. So that is where we have the launch base infrastructure. This is where we launch the satellites from. Then after that we have URSC, that is UR Satellite Center. It was initially called as ISRO Satellite Center, but now the name has been changed to UR Satellite Center. Now this UR Satellite Center basically is where the satellites are developed. So any satellite that we are about to launch, the satellite itself will be developed, manufactured, prepared at UR Satellite Center. Then after that we have SAC, that is Space Application Center. Now Space Application Center is where a lot of smaller components of the satellite is developed. Like for example, the sensors that will be used, or smaller components, etc., that will be used. All those things will be prepared, all the electronic components many times. All these things will be prepared where it will be developed at Space Application Center. So that is basically what the Space Application Center does. Smaller components and parts of a satellite. Then after that we have NRSC. The role of NRSC stands for National Remote Sensing Center. So National Remote Sensing Center is something that will help in understanding and processing of the data that we are receiving from the remote sensing satellites. Now there are a number of remote sensing satellites that are working, and all these remote sensing satellites, we discussed that they take pictures and videos of the Earth. So they would be taking the pictures and videos every given second, and then they keep sending all that data to the National Remote Sensing Center. And it's the role of the National Remote Sensing Center to process all that data and use all that data, make that data useful. So that is basically what National Remote Sensing Center does. So basically this is for processing of remote sensing data. Right. So this is basically what it will do. And then after that we have SSFC, that is Human Space Flight Center. Now this Human Space Flight Center is a new addition. All these other units that we are discussing, all these units have been functional for a very long time. But this HSFC is something that has come into existence only in 2019. And this largely is for taking care of any human space flight that you might take. So for example, the Gaganyaan mission. So all the operations and everything related to Gaganyaan mission is being taken care of by Human Space Flight Center. And that's why even if we plan anything for the future, all the future human space flights also will be taken care of by Human Space Flight Center. Human space flights, including the Gaganyaan mission. Right? So that is basically what it is going to do. Now, apart from that, there are two more units which are important. You have ARIC-6 and NSIL. Now, ARIC-6 and NSIL both basically are called as commercial arms of ISRO. They are called as commercial arms of ISRO. There are subsidies or selling certain products, buying of certain products, all these kind of things will be taken care of on ARIC-6 and NSIL. Now, in this scenario also, ARIC-6 has been around for a very long time. I think it was 2003 or 2002 when it was made a part of ISRO. And NSIL again is a new addition. And NSIL is something again added in 2019. And then question was also raised that if ISRO was already present, then what was the need of NSIL? Why did we need an NSIL? That's already was functioning as a commercial arm of ISRO. So some amount of controversy also happened here. That why do you need a physics if NSIL was already present? So then even the government have given the reply in the appointment saying that ANX is something that we supply based. This is what they had said. That ANX will be supply based and NSIL will be demand based. So ANX will be supply based and NSIL will be demand based. Now what do we mean? What's the meaning of supply based and demand based? So what basically they said is that ANX is going to take care of anything that we already have. And if something comes to us and asks for it, then ANX will be responsible for it. But if there is a new request, something that we don't have, but we will have to make it for somebody, or something that we have manufactured for somebody, then in that case, NSIL will be responsible. All the private dealings, NSIL will be responsible. So it will take care of all the supply-based areas and NSIL will take care of the demand-based areas. So this is basically what the government has said. So supply-based means that's something that you already have, right? So it's like a shop that you go to a shop and you have gone there buy a soap. So the shopkeeper will only be able to give you the soap that the shopkeeper has. So you simply go there and buy it. So that's the role of ANX. In NSIL, request based. That you go to somebody and say that I need this specific soap, make it for me. So that is something that will be taken care of by NSIL. So that is what they said at that point in time. That how the work will be divided between ANX and NSIL. So this is the official answer. Then there is the unofficial part of it as well, where it is believed that there are certain issues that ANX is already fighting. There have been certain problems that has run into. There are a lot of losses that also it has incurred because it got not work properly. And that is where government was of the view. And then there are certain legal cases also that is involved in. So the government thought, let them fight their own battles. We'll have NSIL and NSIL will start taking care of everything else. But you can't write this examination. You can't write this exam. Just for the exam, just remember, and ANX is supply based and NSIL is demand based. You cannot say anything else. So but this is what is also believed that India is moving very fast. I mean India is growing very fast on the space sector. They don't want any packages. They don't want we don't want fights these kind of things. That's why on the side we made another organization to take care of it. So That is basically the difference between ISRO and SIL. Then after that we have in space. Now the role of in space particularly is to work with the private sector, help the private sector, help with the promotion and authorization of the private sector. So that is basically why space has been established and has been established just a couple of years back, 2020. 2020 is when in space have come into existence. So that's why in space basically is what? It's Indian National Space Promotion and Authorization Center. So that's why it basically is going to help the private sector. So help in the growth of private sector in space technology. So that's the basic goal of it. So that's why in space and SIL will work together. They'll work together because we also discussed about SSLV. That SSLV right now is being managed by NSIL. And we discussed, I showed you that is the clipping, that SSLV is going to move the private sector. So that is where we see that NSIL in space, all these are working in tandem and helping in the growth of the private space industry in India. Right. And that will obviously help in a lot of ways and help develop a better space market in India as well. So that is basically how the organizational structure of ISRO is. If you see all these centers of ISRO, you find that most of the centers of ISRO are located in the southern part of the country, South India. Most of them in Bengaluru, a lot of them in Bengaluru. Apart from that, so for example, we discussed about URS, so URS is here, LPS is here, the headquarters of ISRO is also here. Then after that, Vikram Sarabhai Center is something that is in Tirunelveli. And then apart from that, the launch that we do, the launch is done from Sriharikota. So you see that all these centers, they are all located in the south. Only one center is in Ahmedabad, that is Space Application Center. It's only you can say one very important center which is in the north. Now why so? The reason is done from the south. The launch is done from Sriharikota. Just imagine if the rocket or the launch vehicle and satellites were all being prepared in Delhi, and then you will have to bring them from Delhi to Sriharikota. It will be a mess. It will be a logistical mess. So that's why all these centers that they are located here, and so that movement and logistical support can be provided very easily. Now when it comes to all these centers, so you don't even need to know where exactly all these are situated, but it's easy to remember if at all if you want. Now, when it comes to all these resources, there is something else that we need to understand that we discussed that you have Sriharikota, and Sriharikota is situated right here. Right. If you see this, Sriharikota is situated right here. So this is where you have Sriharikota. All our launches right now they are done from Sriharikota. But apart from that, we are developing another spaceport, another launch base in Kulasekharapatnam. And that Kulasekharapatnam also has been in the news because of that. That there is a second launch pad that we are developing, and that's being developed at Kulasekharapatnam. Now you have to understand why. Why are they developing something here? What's the reason? When it comes to the launches that there are a couple of things that you should know about the launches. Right. Now whenever you do the launch, there are two things about the launch. One, that the launch is always done towards the equator. Launch always done towards or near the equator. Let me write here, it will be less confusing for you. near the equator. So this is the question, why do we do that? And secondly, the launch is always done from the east coast. Now the question arises, why? Why do we do this? So just understand both of these scenarios. Why exactly do we do that? Now when it comes to the launch being done near the equator, why do we do the launch from near the equator? The reason is simple, that when we are near the equator, and do you know? I mean, let me ask you first, that you know the reason that why do we launch near the equator? Some of you have the correct answer. Maybe for more. That's this is the rotational period, rotational speed of the Earth near the equator, and near the pole is lesser. Alright, near the pole is lesser than this. So near the equator, the rotation period is highest. We want to take the advantage of the rotation of the Earth. Right? We want to take the advantage of the rotation of the Earth, and that's basically why we do that. And yes, the reason is Coriolis force. So this is basically rotational speed highest at the equator. So we try to take the advantage of that speed while launching the satellite. So that's why the launches are always done near the equator. So it's not only about rotating that others also they try to place their launch bases as close to the equator as possible. So alright, so that's launches are always done near the equator. Now why being done from the east coast? Why the launches are done from the east coast? Yes, you are the correct answer. Lesser gravity also is the reason. Yes, lesser gravity is also the reason. So okay, let me write that. Basically, what happens that diameter of the Earth at equator is larger, which is bulge at equator as compared to the poles. So that's why the distance from the center to the equator is more at the equator as compared to the poles, and that's why the gravitational pull is less. So that also becomes the reason. Let me rewrite this also. Gravity least at equator. Right. So yes. So you are also given the correct answer. Why we launch from the east coast? Because launch is also launch always done eastward. Right. Always done eastward. Why? Because the Earth rotates from west to east. Correct. Now, because the Earth rotates from west to east, we basically apply the concept of the relative motion here. That relative motion concept, if you know, the relative motion concept says that if you are in the same direction, then the relative speed will be a difference of the two speeds. So you will have subtract the speed, so speed is lesser. But relative motion wise, when you are in the direction, the speed will increase. So you'll be able to get hold of, be able to get the advantage of the relative motion. So because Earth is rotating from west to east, we launch eastward. So when we do that, what happens is because of that, we will be able to gain that speed. We'll be able to take the energy of that speed. So your fuel consumption will be less. You will be able to gain the required speed with lesser amount of fuel. So that is basically what happens here. So we can gain the required speed with lesser fuel. Right. So that's why the launches are always done on the east coast. Because launching towards the east, let's say we were using the west coast. Let's say we go and set up a launch base. Let's say on Maharashtra coast or Karnataka coast or maybe Goa if we want to. And we set up our launch base there. And from there we are launching eastward. It would simply mean that you are going to fly over India. You're going to fly over the Indian landmass that can be dangerous. If at all or by any chance, by accident, if let's say any launch fails, and what if it falls on the Indian landmass, that would be a big loss of life and lives for us. So that's why not take that chance. We always launch on the eastern coast. So that simply go into the uh, uh, into the way of water or into the places which are not populated. So that is pretty much the reason. Or we go further than more tip. Now why in this scenario why the Visakhapatnam? Why we launch from here? Because see when we launch the polar satellites, the polar satellites have launched southwards. So if let's say from Sriharikota we directly launch southward, it would mean what? That we have to fly over Sri Lanka. Now, not only Indian lives matter, Sri Lankan lives also matter. So that's why we don't want fly over Sri Lanka, right? So in that case, what we do? We don't take this path. We go like this. We take a southeastern path instead of taking a southern part. What then happens? You are increasing the path length. You are increasing the total distance. You have more fuel. But if we are at Visakhapatnam and we are launching polar satellites from here, we can directly go southward. Right. We can directly go southward. So then in that there's no landmass coming in the way. And then again we will be able to save the fuel. And that is the reason why Visakhapatnam has chosen for a second launch base that is built. So that's why. So that's why we see that also has been in the news. That India has been working on it. And it's not new news. It's not that you see that this is an October news, but it's not that it has been there in November. It has been almost 10 years back. 2013 is when the discussion started, and now that acquisition is happening in the region, and we are trying to build our launch base there. Right. Now, coming to the last part of the discussion, and this is about space-based debris. Now, when it comes to space-based debris, space-based debris, also sometimes called as space junk, is anything or any man-made article, any piece of machinery, any leftover things, any satellite which is hung, all these things which are left in space. So that's called as space debris. The waste that I have basically generated in the space is called as space debris. Now it can be anything. It can basically any large pieces of objects as well. So for example, if you see that 7% of everything is all the operational satellites, whereas you have 65% of non-operational objects, meaning these are dead satellites. Almost 65% of all the space are nothing but dead satellites. And then there are 28% of fragments, very small lumps, small pieces. So they make almost 28% of this entire segment. Now, in this particular scenario, when you look at space debris, we say that space debris have become a bigger challenge by day. Because right now when we look at simple numbers, we see that there are more than 4,000 active satellites, almost 3,000 dead satellites. And then apart from that, there are so many pieces of space junk also that we have. And then there are a lot of debris, avoidance maneuvers that are being done by every country, including India. So we see that in numbers, these numbers are rising. And that they are becoming a bigger menace where we talk about a concept which is called as Kessler syndrome. Now, Kessler syndrome is something that was proposed as a concept by Kessler, was a NASA scientist. And what he said that the way in which space deliveries increase in the future. And remember, this was 1978, where hardly any space vehicles or satellites, etc. were launched. He said that in the future there could come a scenario where the number of these space junk will be so high that it would block the entire orbit. And there would be too much space junk in the orbit. It could result in a chain reaction where the moon and moon objects collide and create huge space junk in the process to a point where the Earth's orbit will become unusable. That there will be so many or so much of space junk in the orbit that may so happen that let's say one sunset comes and collides with some space junk. And because of that, what happens, it creates more space debris. And all these space debris then be spread in the orbit. They might collide with more outside. So in in this manner, a space junk or a chain reaction of space junk will be created. So much so that it might well make it unusable, make the entire orbit unusable. And this is where we have started heading now. This is where we have started heading now, and that's why today we are looking at leading up this space debris. There are multiple different projects, and there are multiple ways in which all the countries are including India. We are trying to clean up the space debris as much as possible. And the situation is so bad, or has started becoming so bad that some of the scientists have even said that the world's largest waste dump lies in the lower orbit. The lower orbit basically is uh, lower orbit basically is where we see that all the space junk is basically starting to pile up, and lower orbit basically now becomes unusable. And now there is no standard regulation, there is no law, there is no treaty, there is nothing that governs how much of space junk can create. And that's why we see that the amount of space junk that we are creating is increasing. This is one of the data that I came across. This is the data of just a couple of months back. That this is a data and that was released in August 2023. So if you look at this data, you'll see that the number of space jets of three countries, obviously Russia, United States, and China, is the highest. Right? These are the highest of all of them. And then after that, there are other countries which also have their space debris, and they are contributing to space debris. And there are multiple different ways in which the countries are also trying to avoid it. For example, India right now is working on a project called as the liable project named Lagrange. So this project named Lagrange basically is the way in which we will try to clean up our space. This basically is a project to clean up space debris created by India. So that's why we are basically working on all these things. We are working on all these different ways in which we can uh, take care of this space debris. But as you can see that as compared to the number of space debris that three countries, US, Russia, and China is using, compared to that, the countries are nowhere. But still, whatever we are doing, it becomes our responsibility to clean that up. So at least it becomes our responsibility to clean that up. Because unfortunately, there is no, as I said, that there is no international treaty or there is no international law or convention, etc., to govern all these things. So that is why this is day by day has started to become a bigger challenge. And to the point that scientists have started calling the lower orbit as the biggest waste dump of the world. So that's why we also have to look at all these scenarios as well. So this brings us to the end of our first chapter about space technology. Any doubt you have regards to the last half an hour of whatever discussion we had in Cincy? Daily or lines which air or fats were almost identical exhaust fuel. Why can't fly higher in so Sri Lanka? Because we don't want any accidents to happen over the Sri Lankan landmass. Simple. Why that satellite can't shot down? It's very difficult because you lose the control. When satellite is dead, basically you want lost the control of satellite. So after that, there is nothing that we can do. Now yes, when you talk about shooting them down, more than shooting them down, it will be at is shoot them up. Basically, to just push them outside lower orbit so that they can take a free path outside. Can completely ruin your orbit, like you're not launching satellite after that. Can we mention safe forward? Yes, absolutely. We will have to. We know that Russia sends much less to space sector than now having more space station. No, it's not that. I mean, Russia historically has been one of the biggest space markets. So yes, USA right now is a bigger market than that. But US also has been able to control its space agencies up to an extent, which Russia hasn't been able to. Which will try to push it. Japan is working on something which is like a fishing net. It's like a fishing net that will collect all everything. So that's a technology also that they are working on. There's no chance to reuse the satellite will be used once. China and Brazil are very good because China helps Brazil doing their space activities. Just started, no, has started it, we are still working on it. Can we use satellite out of Canada? Yes, we can, but it will be how it will have to use much more fuel. If places that multiple orbitals, and we do that when ISRO has also done that. That we have launched single launch. We have basically launched two satellites like two different orbits on the same launch. So yes, that's possible. Done. So let's move forward to the next chapter, and the next chapter for us is energy. Now, energy as a chapter, first of all, from your prelims and mains perspective, let me tell you that this will be a very crucial chapter. Both in your prelims examination as well as in your mains examination. In both the examinations, energy as a chapter is going to be essentially crucial. Now, also understand why. You will see that in the last 10 odd years, or let's say last 15 years, our discussions on energy or building the alternate sources of energy has increased everywhere in the world, whether India or other parts of the world. Everybody has tried to build alternate sources of energy. Alternate to what? Alternate to coal and petroleum. We are trying to get rid of coal and petroleum as quickly as possible. We don't want to use coal and petroleum because we know the problems. We know the amount of pollution that they cause. We know their role in climate change. So that's why we don't want to use coal and petroleum, and we want to get away from them as quickly as possible. And that is where we are trying to build alternatives like solar energy, wind energy, nuclear energy. So there are multiple different ways in which alternate sources of energy are being looked at by the entire world. And that's why as the topic it becomes a very crucial topic because it will be in the news all the time. I mean, I'm 100% sure that every week you will see at least one article in one way or the other which will be related to energy in one way or the other, right? So that's why energy as a topic becomes very crucial both for your users and your human beings. Now, coming to what exactly are we going to read in this chapter, learn in this chapter. So first and foremost, we are going to learn about all the various different types of energy sources. We'll start with a basic introduction to what energy is, what do we mean by energy, what are the different types of energy, and then after that, one by one, we'll go into the details of all these energy types. We'll discuss first about the non-renewable energy sources, like what is coal, what is petroleum, shale gas, and all these kind of things. First, we'll discuss them. Then we'll move on to the renewable energy sources, where we'll discuss about solar energy, wind energy, biofuels, etc. And then towards the end of the chapter, the last part of the chapter will be about nuclear energy and nuclear technology, where we discuss about nuclear fusion, radioactivity, and all those kinds of things. So that is basically how we are going to look into this chapter. Now, first and foremost, when we say energy, what do we mean by energy? Now, our basic understanding of energy and physics understanding of energy are two different things. So you know that if you have to do something, you will need energy for that. So for example, if I have teeth, I should have eaten something. Otherwise, it will become almost impossible for me to survive the entire day without eating, without having that energy to keep eating. Right? So energy basically provides us the capacity to do work. But when we say work in physics, the definition changes. We say that work in physics basically is the force that we apply in the direction of motion. Then in that case, work is done. So for example, me sitting here or standing at one place and delivering the lecture. If you are a physics student, you will say that I have done nothing. That I was doing nothing for these 3.5 hours because my discipline was zero. I did not move. I was just at one place delivering the lecture. So then because the movement is zero, simple definition for work is force multiplied by distance. So because distance is zero, you will say that that done is zero. So I would have done nothing. And I can say the same thing for you. That if you're just sitting at a study table and making notes or studying, I can also say that you do nothing for these 3.5 hours. So physics definition of work is different. But here we are not bothered about the physics of work, but rather we are talking about the sources of energy. Where do we get the energy from? And energy that is basically the currency of the world right now. Energy is nothing less than currency. The countries that have their energy sources sorted are the developed countries. If you look at them, these are the countries which developed their energy sources since the Industrial Revolution time. And that's why they became the developed countries. The countries which were late, they are the developing or let's say the underdeveloped countries. So that's why we know that this is what energy is. Now, when it comes to energy, there are two ways in which we classify energy. One on the basis of renewable and non-renewable energy, and second on the basis of conventional and non-conventional energy. So first and foremost, we try to understand what do we mean by renewable energy and what is non-renewable energy. So renewable meaning you can renew them. That's why renewable. Now when I say renewable and the fact that you can renew them, if let's say you have a source of energy that you can renew in like 50 years or maybe 100 years, can I say that it's a renewable energy? Should I say that it's a renewable energy? Faster than I can consume. Meaning, uh, the rate at which we exhaust them should be lesser than the rate at which we are using them. So basically, in a manner, you can say that renewable energy is the source of energy or the kind of energy in which the rate of consumption, right? So this will be the rate, the kind of energy where the rate of consumption is lesser as compared to the rate at which you are able to get them. So for and these are the resources that will last us forever, right? So rate of consumption is less than the rate of replacement. Just understand this, that the replacement is happening faster, right? The rate of replacement is faster and the rate of consumption is slower. Then only in that case I can say that this is renewable energy. So we should have more than we can consume. So for example, solar energy. Solar energy is a source of energy that we have in abundance and it is going to last with us forever. Right? For as long as the earth exists, solar energy exists. If tomorrow there is no solar energy, forget life on earth. Right? As simple as that. So that's why solar energy is renewable. Same goes for wind energy. The factors that generate wind, they are geographical and geological factors. So it's not that they are going to go away. They're not going to go away. Right? So that's why wind energy also is going to last forever. For example, one of the sources of wind generation is rotation of the earth. What if the Earth's rotation stops? What will happen? We'll all fly off. Right? So that's why it's not going to stop. Correct. So that's why wind energy also is going to last with us forever. Geothermal energy, biofuels, the same case. That they are going to last with us for a very long time. So that's why they are being called as renewable energy sources. On the other hand, we have coal, petroleum, and natural gas. And all of them are being classified as non-renewable energy because their replacement rate is far replacement rate is slower than the consumption rate. So just to give you a simple mathematics, coal. Largely we started using coal, you can say at a commercial level since industrial revolution. Right. Before industrial revolution, it's not that coal was not being used, but not at a scale that we started using after industrial revolution or since the industrial revolution. Correct. And how much time do you know? How much time it has taken for coal formation to happen? Any estimates? If anyone has, how much time does it take for formation of coal to happen? Yes, millions of years, right? Almost up to 300 million years. So something for which formation took 300 million years, we have almost exhausted it in 300 years. That's the kind of difference that we are talking about. That's something where the formation happened in 300 million years, we exhausted it, almost exhausted it in just 300 years. So for example, the estimate for India, the estimate of India is that India has like 3 years, almost 140 years of coal left. The rate at which we are consuming coal, we just have 140 years of left. That's it. After that, we are not going to have any coal. And then we'll have to actually look for other source of energy. And that's the reason why we have started looking for other source of energy. Yes, the primary reason also is air pollution, other forms of pollution, climate change, etc. But there is another reason that if we keep on using coal at the rate that we are using it, will not left with any coal in the next 130, 140 years. Same goes for petroleum. Formation has taken more than 250 million years and exhaustion like 300 years. So that is basically why we are calling them as non-renewable source of energy. So on one hand you have renewable energy, on the other hand you have non-renewable energy. And then there is the third source of energy, that is nuclear energy. Now is nuclear energy renewable energy or a non-renewable source of energy? Is it renewable or non-renewable? So everyone who has given the answer has given correct answer. It's renewable and non-renewable, or you can say that is neither renewable or non-renewable. So if a question comes in your prelims examination, then leave the question and go to the next question, because we cannot classify it as renewable or non-renewable source because there are various reasons. And we discuss those reasons in detail when we go to nuclear energy. But for now, just understand that classifying it as renewable or non-renewable is very difficult. So we can say renewable if, let's say, we start using nuclear fusion. And we'll discuss what is nuclear fusion and all that. But if we start using nuclear fusion, we perhaps can say that this is renewable. But right now, as of today, we are largely dependent on uranium for nuclear fission. Uranium is limited, so that's why it is non-renewable for now. So for now it is non-renewable, but in future we can make it renewable. So that's why it's very it's a topic of debate whether to call it as a renewable energy or a non-renewable energy. So that's why we'll not look for them. Now, the second way to classify energy is on the basis of conventional versus non-conventional energy. Now, conventional energy is basically something that we have traditionally used, that we have been using for a very long time. That's conventional. Non-conventional, something that we discussed of late, something that we have developed only, let's say, in the last 40, 50 odd years, we started using it commercially. So, for example, petroleum, natural gas is called as conventional energy, solar energy, wind energy, geothermal, biofuels, etc., non-conventional. So largely you can see that the renewable sources of energy are non-conventional and conventional sources are non-renewable. But that's not a rule. It's not always the case that they always have to be the same. Because there are sources which can be classified as non-conventional as well as non-renewable but at the same time. For example, shale. And we'll discuss about shale gas separately. But shale gas can be said to be non-conventional but at the same time non-renewable as well. So that's not a rule that non-conventional will be renewable and conventional will be non-renewable. There's no rule as such. So this is how we have been using it. I mean, for example, when we talk about coal, we know that since industrial revolution we have been using coal at a very large scale, at commercial scale. But it's not that before that we were not using coal. You'll see that if you go to medieval history of Europe, you'll see that there were rulers, there were kings who had banned the use of coal in their kingdoms because of air pollution, because of smog situation. Smog is not new and it's not only in North India. Smog is something that if you go back to medieval London, you'll see that smog situation was a rising there as well. And because of coal was the primary reason there. So burning of coal and everything, it actually became a reason. So that's why these are conventional. Now to start with, basically, we'll start with all the non-renewable energy sources first, and this is where we started coal. Now, talking about coal, first and foremost, what we know is that coal is a fossil fuel, and it's a fossil fuel called as a fossil fuel because we get it from the fossilized remains of prehistoric vegetation that originally accumulated in swamps and peatlands, basically in the wetlands. In a manner, you can say that in swamps and wetlands is where they would have started. This is where their journey would have started from. That the vegetation that was growing in the wetlands, for some reason, it could be seismic reasons, it could be other reasons. For some reason, any geological reason, it started getting submerged under land. And as it got submerged under land, this is where it was subjected to high temperature and pressure. Now, with higher temperature and pressure, it started a chemical conversion. There started a chemical conversion, and ultimately all these organic sources, all these vegetation, it got converted into coal. So this is what we believe. This is basically what we believe, that this is not believe. This is what we have estimated, and these are the evidences that we get, that it would have started from prehistoric vegetation that got submerged under land, and as it got submerged under land, it was subjected to high temperature and pressure. And under these situations, conditions of high temperature and pressure, it ultimately got converted into coal. So this is basically how we believe the coal formation might have happened, starting almost 360 million years to 290 million years ago. Now, when it comes to coal, we see that there are different types of coal, right? There are different types of coal, and all these different types of coal, basically depends on how much temperature and pressure they might have been subjected to for how much amount of time. So for example, for very long time, if subjected to high temperature and pressure, anthracite would have been formed. With little lower temperature and pressure, bituminous, even lesser lignite, least amount of temperature and pressure, with very small amount of time, peat. So these are the types of uh, these are the types of coal. So if you see this, there are four types of coal: peat, lignite, bituminous, and anthracite. If you look at peat, what you see with peat is that peat has a very woody appearance. It looks like a bark of a tree. The reason is that complete conversion into coal did not happen. It was not subjected to very high temperature and pressure, and because of that, a complete conversion into coal could not happen with peat. So that's why it is said to be the uh, least variant of coal with least efficiency. Alright, the pollution levels are high, efficiency is low, does not burn very well. So much so that if you go to coal ministry website or coal India website, you will see that they do not even recognize peat as coal. They say that peat is peat, coal is coal. Peat is not coal. So because peat is very low in its very bad in its nature, because it's highly polluting, very low efficiency, and because of that, peat is not even considered as a primary fuel or even a type of coal at times. But technically, it is a type of coal. Then after that, there's lignite. Now, if you see lignite has a brownish appearance. As you can see, that it looks like a brown stone. That's why sometimes it is also called as brown coal. The name that is given is brown coal for lignite. Now, with lignite also, it does not really have a very high efficiency, but at least it's better than peat. Can be used for electricity generation, can be used as domestic fuel, can be used in various industries, but it's not recommended. It's not the primary source that is sought. So that's why we see that lignite is not primarily used, but sometimes it can be. And then we have bituminous next. Now bituminous is also called as industrial coal. It is also called as industrial coal because industrial coal, basically, why? Because in most of the industries we use bituminous. In electricity generation we use bituminous. In iron and steel industry we use bituminous. In other chemical industries also, in fertilizer industry also, we see that bituminous coal is used. So that's why bituminous is the most important variant, most widely used variant, and also called as the industrial coal. Then after that we have anthracite. Anthracite is the best variant of coal. Efficiency is very high, pollution levels are very low, so it's the ideal coal. But the problem is that we don't really have a lot of anthracite. India specifically, India does not have a lot of anthracite. We have a lot of bituminous, but not a lot of anthracite. So, so that's why anthracite is not that usable for us. There are other countries, for example, US has a lot of anthracite. Uh, uh, China has a lot of anthracite. Other countries have significant amount of anthracite. India does not. India has a lot of bituminous coal. So if you look at all these different variants of coal, just a comparison between all these, carbon content in peat is very low. So it is just, you can say, even lesser than 40%. It has less than 40% carbon, and that's why the amount of impurities is very high. Amount of impurities is very high, and that's why the efficiency is low. In case of lignite, generally speaking, it has between 40 to 55% carbon content. So that's also low. So that's why efficiency is low and the amount of impurities is high. In case of bituminous, largely between 55 to 80%. 55 to 80% carbon. So it has high efficiency and low amount of impurities. And in case of anthracite, generally it is between 80 to 95%. So it has a lot of carbon and very less amount of impurities, and that's a very high efficiency. Now, when you look at the use Generally, we see that the use in the industries will be of bituminous. Then apart from that, when it comes to peat, for example, it can be used in agricultural purposes, in water filtration. Agriculture, for example, if you see peat, because peat has organic nature, obviously you have carbon there. So because it is organic in nature, it can be used to enhance the quality of the soil or enhance the quality of wherever you are growing plants. Even if you go to Amazon, I think you will get peat, because in flowering, I mean in gardening also, peat has a very good value. So that's why peat is used there, largely used there. Then in case of lignite, it can be used as industrial coal. It can be used as as a source of domestic electricity as well, but avoid it. Bituminous, the most important one, and then you have anthracite, which again can be used in smelting industries and in heating systems also. It can be used. Now, when you look at the distribution, you'll see that these three states, Jharkhand, followed by Odisha, followed by Chhattisgarh. These are the three states where the amount of coal reserves is the highest in India. Now, apart from that, also there are other states as well. It's not that there are only these three states. If you see this, the central part of the country, Jharkhand, Odisha, Chhattisgarh, plus after that, West Bengal, Maharashtra, Madhya Pradesh, Telangana, and Andhra Pradesh. All these states also have coal reserves. Apart from that, also parts of Uttar Pradesh and very small parts of Bihar as well. These are also the states where you have coal. So all these are the areas where we primarily find bituminous. This is the primary area of bituminous coal. Right? This is the primary area of bituminous coal. Now coming to the northeastern states, especially Assam, Meghalaya, plus parts of Arunachal Pradesh and smaller parts of the other northeastern states as well, we see that this is the part where largely we find peat. So see, when I say that bituminous is found here, it does not mean that it does not have lignite or does not have peat. It does have it, but largely it has bituminous. Same goes for the northeast as well. That in northeast you have a lot of peat, but also other kinds of coal is also found there. Then apart from that, these areas in Rajasthan, Gujarat, Tamil Nadu, Puducherry, even small parts of Kerala, these are the areas where you have large deposits of lignite. These are the lignite areas of India. And then this part of Jammu and Kashmir, this is the part where we find anthracite, but in very small quantities. So this is basically how the distribution of coal in India is. But largely, just remember that these three states are very crucial: Jharkhand, Odisha, and Chhattisgarh. These are the top three states when it comes to the coal reserves in the country. Now, talking about coal, one thing that becomes very crucial for us to understand is the impurity part. Because when you are burning coal, when the combustion of coal happens, obviously a lot of impurities will also be produced, because you have a lot of impurities, and all these impurities, the leftover basically is called as the ash. And as you see in the picture, you see that there is one picture where you see that there is very fine powdered material. This is basically something which is called as fly ash. This is called as fly ash. And this part, the bigger parts, bigger chunks of leftovers, this is called as bottom ash. Right? So fly ash and bottom ash. Now, in case of fly ash is a bigger challenge for us, because bottom ash is bigger material, right? So what happens is that it just gets stored at the bottom of the furnace. So getting rid of bottom ash is not a big challenge for us, but fly ash is a bigger challenge. It's being called as fly ash. Why? Well, flies, because it's very light in weight, so it can come out of the smokestacks, etc., and can deposit in the air nearby, deposit on the water bodies nearby, on soil nearby. So it can cause water pollution, air pollution, land pollution, all these kind of problems. So that's why fly ash becomes a bigger challenge, and we need to take care of this ash. So when we talk about the ash, basically is the residuals. The residuals that are left after the combustion is completed, that is called as coal ash, or there are different types of coal ash. Now, when we talk about ash, it does not only contain some basic impurities, but it does contain lead, arsenic, mercury, cadmium, and even traces of uranium. Now, all these metals or all these elements, these are harmful. These are harmful elements, and that's why they can significantly cause pollution, health hazards, everything. So that's why we have to get rid of this ash. We need to get rid of this ash. So first one is fly ash, and as I told you that this is a fine powdery silica material, and which is basically created when fine coal or pulverized coal is burned. Now, pulverization basically is the process that is used, because see what happens is that when we mine coal, there are big blocks of coal, big stones of coal, and when they are fed into the thermal power plant, that is where they will be crushed into very fine powder, of coal. This basically is the process which is called as pulverization. So pulverized coal is that's why fine coal, the powdered coal. This is the fine powdered coal. So basically, this is what fly ash is, which is produced when the pulverized coal is combusted. Then after that, you have the bottom ash. Bottom ash is a more coarse, COARSE. It is a more coarse ash particle, bigger particles, which will deposit at the bottom of the furnace. So easier to take out, easier to get rid of. Apart from that, we see that there is also something called as boiler slag and flue gas desulfurization material. Now, these are not significant problems. They are also produced, also can be called as a kind of impurity or the ash, but producing very less quantities. So that's why they are not big problems for us. So boiler slag basically also can be called as a kind of a bottom ash only, which is largely in molten or partially fused ash part. So it will also have silicon dioxide, aluminium oxides, calcium oxides, iron oxides. So they basically also are kind of bottom ash and can be removed. And then we have the desulfurization material or flue gas desulfurization material. So basically this is the leftover when we start taking care of the sulfur dioxide. When the removal of sulfur dioxide is done, there is a wet sludge that is basically produced here, and this basically is called as a flue gas desulfurization material. So again, boiler slag and flue gas are not big challenges. The biggest problem is fly ash. So that's why the disposal and the recycling of fly ash becomes very, very crucial. Now, how do we dispose it? Disposal of fly ash can be done either through landfillings, that you just dig up the land and you keep all the fly ash there and you just cover it. Either that, or all the abandoned mines are used. The mines where mining activities have already happened and they're not in use anymore. Those abandoned mines are where all the fly ash is just kept. So that's one way to dispose it. Recycling wise, there are multiple ways. So for example, they can be used in mixing with cement. They can be mixed with cement. They can be mixed with bricks. If you have seen these kind of bricks, these bricks basically have fly ash mixed with it. So in bricks they can be used. In cement they can be used. In different construction material they can be used. In even making the roads with the hot mix where the roads are constructed, there also fly ash can be mixed. So in all these ways, fly ash can be taken care of, fly ash can be recycled. Bottom ash, when it comes to it, bottom ash is also used in the removal of snow. Controlling the snow on roads, removal of them, because it is a very good absorbent. So that's why it helps in the removal of snow. So in this case, recycling or disposal of all these ash that we are producing from coal, that can be done. So there is something again that has been in the news for the last couple of years, at least for the last 2-3 years, it has been constantly in the news, and this is coal gasification. Now, when it comes to coal gasification, understand what we mean by coal gasification. So, coal gasification is the process where we gasify coal. right? We are gasifying coal. So gasifying coal means that we are converting coal into gas, a kind of gas. So you'll say that how is this process different? I mean, there also we are burning coal. Here also we'll have to burn coal. How is it different? Burning of coal normally that happens in, let's say, a thermal power plant or an iron and steel industry. That's a basic combustion at a lower temperature, at 300 degrees Celsius, 400 degrees Celsius, and so on. That's the basic combustion of coal, that you feed it to the furnace and you just burn it. And it will burn, it will convert into heat energy and you use that heat energy. In case of coal gasification, we convert coal into something called as synthesis gas. Synthesis gas, something which is also called as syngas, in other words, also called as syngas, also called as synthetic gas. So if you see any one of these terms, synthetic gas, synthesis gas, syngas, just know that we are basically talking about the same thing, where the gasification of coal has been done, and this happens at a higher temperature. The temperature that we need to achieve for gasification of coal is 1200 to 1500 degrees Celsius, whereas the normal combustion process takes place at 300 to 400 degrees Celsius only. So here we produce syngas. And what is this syngas? Syngas is a mixture of hydrogen, carbon monoxide, and small amount of carbon dioxide. Small amount of carbon dioxide, larger amount of hydrogen and carbon monoxide. So this mixture basically is called as syngas. Now there is no fixed ratio. It's not that this much percentage of hydrogen, that much percentage of carbon monoxide, and so on. No. There are multiple different types of syngas also. These are all called as industrial gases. So there is water gas, producer gas, coal gas. I'm not going there, but these are all called as syngas. And various industries, they use different types of syngas. So syngas basically is the gas that you produce while combustion of coal happens at very high temperature and pressure. Alright. So gasifier basically is a high pressure vessel which reaches the temperature of around 1200 to 1500 degrees Celsius in the presence of steam and oxygen, and temperature, the high temperature and pressure basically they cause the coal to break down, and this is where they convert into syngas. Now why is this in the news? Why are we talking about this syngas or coal gasification as a process? Because coal gasification basically is something that the government has started taking very seriously. So as you can see in this news, that government is considering rupees 6,000 crores of coal gasification scheme, where we are looking at 100 million tons of coal gasification to be done by 2030. So this is something that the government has been working on. Now, a couple of years back, you will see that for the first time in the budget, I think it was budget 2021, when the government started talking about coal gasification, that India is going to set up coal gasification plants for thermal power plants and also for other industries. We'll start building or we'll start constructing coal gasification plants. So that is basically the announcement that was done, budget was allocated, and now we see that coal ministry has come out saying that they'll be investing rupees 6,000 crores on coal gasification scheme, and they'll be looking for almost 100 million tons of coal gasification by 2030. Now, why? Why are we spending so much on coal gasification? So try to understand the advantages, that why exactly do we want coal gasification. So first and foremost, what we see is that coal gasification will give us cleaner burning. The pollution levels from coal gasification is very low. So first and foremost, the ash production is very low. All right. So that's why we see that pollutants like sulfur dioxide, nitrogen oxides, particulate matter, ash, we see that all these things will be very, very less, and that's why this burning will be cleaner. The combustion of this coal will be much cleaner as compared to the normal method that we have been using traditionally. So that's the first thing. Secondly, the efficiency. It gives us a lot better efficiency. For example, the basic normal conversion of coal that we do, that has an efficiency of around just 33%. Whereas coal gasification can convert up to 95% of energy in coal. So efficiency is very, very high, right? Efficiency is very, very high, almost up to 3 times of the efficiency that we have with the normal processes that we have been using. So that's the second thing why coal gasification, because efficiency is very good. Then it is also versatile. Versatile meaning that this syngas, it can be used in variety of ways. Syngas can be used in electricity generation, in heating systems, in production of chemicals and other products, even in fertilization production. Sorry, for fertilizer production. So in all these cases, we see that syngas can be used. So that's why from that perspective, it becomes very, very crucial for us. Similarly, we are also saying that it will help us in enhancing our energy security. Now, when we say energy security, means that we basically try to reduce our dependence, energy dependence from other countries. For example, let's say with petroleum, we are highly dependent on other countries, whether it is West Asian countries or whether it is the US or Russia or Australia or any other country for that matter. So we know that we are dependent on all these countries. Now, if we increase our efficiency, we'll not have to depend on a lot of these countries. So that's why from that perspective, it will help us in enhancing our energy security. So that's why we are talking about this factor as well as an advantage of coal gasification. So that's why coal gasification has all these advantages, although there are issues as well. It's not that it does not come with its issues. There's a wonderful article actually that was published last year in Down to Earth. Read this article if possible. It's an easy article to read. Down to Earth, you just Google it, right? Just go to Google and just Google coal gasification. Coal gasification down to earth. Just write this much. You'll get an article that was published in Down to Earth, and that's why it's available online as well. Read it as an assignment. You'll understand this entire article, but it gives you the other side of the story, that we are talking about the advantages and all these things that we see, and so much of investment that is happening. But at the same time, there are problems as well. That first and foremost, a simple thing, we need to reach the temperatures of 1200 to 1500 degrees Celsius. That does not happen magically. You'll have to spend energy to do that. So this efficiency that we are talking about, that it has a very high conversion rate, you are also spending some amount of energy to get there first, right? So that is not something that we are considering while talking about the advantages. So that's why there are all these kind of shortcomings, you can say. All right, there are all these shortcomings that we have, and that's why we need to understand this from the perspective, the other side, the environmental side of it as well. So just do that. Please read this article. It's a simple article to read, but it's a very detailed one. They have given the entire thing about what happens and how we need to take care of it. All right. So look at this question. This question was asked in your paper. Simple question. Produced by the power plants using coal as fuel. Which of the following statements is or are correct? First, fly ash can be used in the production of bricks for building construction. We saw the pictures as well, so that's correct. Fly ash can be used as replacement for some of the Portland cement in the contents of the concrete. So that's also correct. We discussed that you mix it with cement also. Fly ash is made up of silicon dioxide and calcium oxide only and does not contain any toxic elements. The entire point of our discussion is toxic elements, right? So you can't say that it does not contain any toxic elements. So it does have a lot of toxic elements, and that's why 3 is wrong. So correct answer will be A, that is 1 and 2. And also remember that whenever you see these kind of words, when you see something like only, we call them as extreme words. And always be aware of extreme words whenever you see, wherever you see them. Always these kind of words, they, you will see that, I'll not say 100% of the times, but 90% of the times they will be wrong. So that's why at least read them multiple times. That if you see any extreme words like this, so only, all, none, definitely, completely, all these kind of terms, if you come across, just remember that these are all extreme words, and you have to go with caution whenever you see these kind of words. All right, and we'll take a lot of examples where you'll see that wherever we have these extreme words, more often than not, they are wrong statements, and that's the case here as well. Right? So, okay, let's stop here because we are already done, almost done with the time. We'll start with petroleum in the next class. First and foremost, okay, one thing. In space technology, whatever we discussed, apart from that, there is something else also that you should read, and this is India's space policy. There is the new space policy document, Space Policy 2023. Now, I have asked the team to attach the document along with the PDF of today's class. So please go there. There I have highlighted the important points because that's completely factual, nothing for me to explain. But there are some key points, and I've highlighted those points and I've given them to the team so that they would attach it along with the PDF for today's class. So just please go through that. The Space Policy 2023 document. All right. So, yeah. So let me show you the leaderboard for today.